Part A of this question asks us to draw the free body diagram for the sphere which is falling. So we can consider this like a real life example, as it's like a raindrop which is just going to be falling. So our first part of the question asks us to draw the free body diagram just when the raindrop starts to fall. So when it just starts to fall, notice that there's going to be no resistive force, especially in this case because our force, F equal to negative kV, is proportional to our velocity, but our velocity is 0, so our resistive force will be 0. The only force which is going to be acting at this point will be our gravitational force. And for part 2 of this question, we have to draw the free body diagram after some time, or once it hits the terminal velocity. So, of course, there's going to still be the gravitational force, and once it hits terminal velocity, what's going to happen is that our sphere or our raindrop is going to be falling at a constant speed. So the net force on this system must be 0 because there is no acceleration. So there's going to be a force of negative k into v acting upward in order to create zero acceleration. Part B of this question asks us to find the terminal velocity of the sphere. So we can now just go back to our free body diagram drawn over here, and recall that I stated that our two forces are going to be equal to each other because when an object is in terminal velocity, it is falling down with an acceleration of 0. So now we can use Newton's second law to write an equation for this. Taking upward as the positive direction, we know that sigma Fy is going to be 0. Since our upward direction is going to be positive, we get minus kV minus m to g is equal to 0. And we can then solve for v. We get minus mg is equal to k times v. And v is going to be equal to negative mg over k. And again, v is negative because our sphere has a velocity in the downward direction. Part C of this question asks us to draw 3 graphs: an acceleration time graph, a velocity time graph, and a displacement time graph, or position time graph. So first up, we have our acceleration time graph, which is shown over here. Now we know that at the very beginning of our journey, you can look back at our free body diagram, we see that our acceleration is going to be negative g. So we can mark a point there. We know towards the end of our journey, our acceleration is going to become very, very close to 0. So we can mark another point right here. Now the only question remains is, how is it going to be connected? Is it going to be a line? Or perhaps it could be curvy. Or perhaps something like that. So in order to think about this one, let us write an equation using Newton's second law for the acceleration at any time. So again, we're going to use something like this, except our object is still going to be accelerating. So we have negative kV minus m into g is equal to m to a. Now we know that a is same as the derivative of the velocity. So we get negative kV minus mg is equal to m times dv over dt. And we can now notice that this equation is a differential equation. and we can solve it. And when we solve it, we're going to get an exponential graph. So this part over here is going to be curvy. So our graph would look something like that, where this is an asymptote. For part 2 of the question, we want to draw the velocity time graph. So our velocity is going to start off at 0. And at the end of our journey, once it reaches a terminal velocity, it is going to end up somewhere here at whatever our terminal velocity is, that is negative mg over k. And again, this path over here is going to be curvy in nature. And the reason for that is we know that the velocity is, the acceleration is the derivative of our velocity. So if this is curvy, we know that this path also has to be curvy. And our final part is our position time graph. So we start off at some position, and that's going to be some height up here. And we're going to reach our terminal velocity at some point, at some position over here, and then we're going to continue going to the ground. So this is going to be kind of like a piecewise function, because after we reach our terminal velocity, we're going to go with the constant velocity all the way to the ground. So this second part is going to be a line. This first part is going to be curvy. Again, it's going to look something like that, with this line acting as our asymptote.